All right, so let's continue on talking about conditional probability. This is the not the next problem. I think it's the fifth problem, so it should be on the third page. So it should copy the front and back. All right, so we talk about testing for the AIDS virus in this table. Doesn't really matter what the table's about, but they give you four different events and then different totals of the events, and then an overall total for the different pieces. So the group here, for example, in the upper left-hand corner would be the intersection of A1 and B1, A1 and B1 at the same time. Test positive and has the virus. This one is test positive and doesn't have the virus. So false positive, if you will. Test negative has the virus is here. False negative, and then test negative and doesn't have the virus. Thinking about just medical testing in general, false positives aren't the worst thing in the world, but you would really hate to have many false negatives. You'd rather be much more accurate on the negative side than the positive side, generally speaking, right? And that's why usually when they run tests, especially for infectious diseases or genetic diseases, things that are particularly rare, if something pops up as positive, they'll run it again to see if it's a false positive. We will have more of a discussion in this along the way. All right, so if we just look at the first two parts where they ask for the probability of B1, what would you look at for the probability of just B1 all by itself there? Okay, yeah, so the total is, oops, wow, that was not what I wanted to do. Still on the, there. All right, so there's 5,000 in the B1, right? Out of how many total? A million, right? Okay, so it'd have 5,000 over a million. Whatever that simplifies to, don't really care about simplifying it at this point. But that's just a straightforward total, number that are in the event, the number that are in B1. And that was why we looked at the total down here, right? Not the individual pieces, the whole thing for B1, and then the total overall that were actually tested. All right. So you can do the same thing for A1, right? What would be the probability for A1? Good. Everybody okay with those two? Looking at the totals? All right. So let's do a couple of the pardon me, a couple of the conditional ones here. A couple of the conditional ones here. So there's a couple of ways to think about it. One is just using the definition that we had before. We had probability of A given B was probability of the intersection over the probability of the total, or the probability of the given, sorry, not the probability of the total. That's the formula, right? So we could do that with the formula, but in this case, it might be a little bit easier to remember that we think about the given information as extra information. It changes your sample space. I could think about this as the number of things that are in the intersection over the number of things, or the number of ways, if you will, that B can happen. This is another way to think about it. Say again? Yeah, these are equivalent to each other because I can transform this into this by just dividing by the size of the sample space. So those are equivalent to each other. Yes. All right. So notice in this case, when we want the probability in part C, it's asking us for the probability of A1 given B2. I don't care about the entire sample space anymore. I only care about, I'm given B2, so the only thing I care about for part C is that column. I don't care about anything else. So what's going to be in your denominator? If that's the column that I'm worried about and absolutely nothing else, what's your denominator going to be? Good, the 995,000, good. What's the numerator going to be? Good. You could have done it, again, using the formula. The probability of A1 and B2 at the same time, well, that would be your numerator. That would be your denominator. And then the probability of B2 would be, this would be your numerator, this would be your denominator. The millions just cancel out in that case. So you could have used this formula as well. You just would have had this over a million and this over a million, and they cancel each other out. What about the other way around? Pardon me. Not the other way around, but the part D. What do we look at for part D? The top row, right? It says we're given A1, so I don't care about anything else except for the top row, right? So what's your denominator going to be if I'm just looking at the top row? Good. And the numerator will be good, 4885. It's a 5. Still a 5. Okay, where we're getting those numbers from? The last part, it asks in words, what do these things say? So let's look at the part C and just see if we can interpret what's being said here. What does B say? The B2 say?
Negative. How many tests positive but don't actually?
Okay, so is this given what? What's the given information?
Given
You don't have the virus, right? And this is you tested positive, right? That's a false positive, isn't it? You don't have the virus, but yet you tested positive. That's a false positive. Good interpretation. The given information here is that you tested positive. This says you do carry it, right? So that would be what we want. Given that it's positive, you actually have it. That's kind of the accuracy of the test, isn't it? If you will. Yep. Yeah. So the first one, what's the given information in the first one? What's the given? You don't carry it, right? And then given that you don't carry it, okay, so that's the given. What's the first part? What's the A1? You test positive, right? So you don't have it, but you tested positive. So that's a false positive. That's what that means. And in that case, that again, we would want false positives happen. We would want to be testing again in that case. Okay. And then the other one would be kind of the accuracy of the test, right? Given that you tested positive, probably actually have it. All right. Any questions about how we computed these things? Right. Well, let's play around with some more of these problems. Let's go back to see if we can just deal with the formulas. Let's look at this. I think this is the second problem, if I remember correctly. They give you lots of information. They give you, even before they start telling you some probabilities, they also tell you some information about the individual sets. They tell you that B and A are complements of each other. So even without the numbers, in particular, even without, say, the second number here, what's true about the probability of A and the probability of B when you add them together? What do you get? 1. Good. Okay. So notice they actually gave you a piece of information that you could have computed, right? They could have told you probability of A and not B, or probability of B and not A, and you would have been able to figure out the other one because they're complements of each other. So it says C intersect D is empty. What do we call C and D when their intersection's empty? Mutually exclusive, right? So looking at this piece, let's ignore the numbers for the time being. If we want the probability of C union D, well, we know a formula for breaking up the union. How can we rewrite the union?
Probability of C, probability of D.
And in general, what do we need to subtract off? Intersection, good. That would be what we would have in general, right? But what do we know about C and D? They're mutually exclusive, so this probability is on the end. This probability here is 0. Good. So we can just write this as probability of C plus the probability of D. Okay so far? Okay. So let's basically, if we can figure out these two values, we're done. We just need to add them together, right? So let's see if we can concentrate on finding the probability of C first. Let's see if we have enough information to figure out the probability of C. So let's use this piece of information right here, where we have the probability of C given A is 1/2. How can you rewrite probability of C given A? Good. Probability of the intersection over the probability of the given, right? We agree? So far, so good? All right. Do we know probability of A? Yeah, they told us it's 1/4, right? So what's the probability of probability of C intersect A going to be then? If the probability of A is 1/8, or 1/4, I'm sorry. Guess I said the answer. It's going to be 1/8, isn't it? Because you have a 1/4 here in the denominator, I just multiply it to the other side. So 1/4 times 1/2 is 1/8. So the probability of C intersect A is 1/8. We should be able to do the same kind of thing for C intersect B. So we're given that the probability of C intersect B is 3/4. Do the exact same thing like we did in the first part of the, well, we just did about 2 minutes ago, not even 2 minutes ago, a minute ago. Use our formula to rewrite the conditional. And do we know the probability of B? Yeah. Our probability of B is 3/4. So I'd have a 3/4 in the denominator here. Multiply it to the other side. What do we end up with for the intersection of C and B? 9/16. It's good. Those two parts okay? I mean, they're identical to each other, just we change the A to a B, right? Literally the same process. I claim now we know what the probability of C is. let's think about what's going on here. What does this say? Just as a set, what does this say? What? Yeah, everything that's in both C and A. This one says, let's C and B. What relationship do A and B have again? Complements. So this is everything in C that's in A. This is everything in C that's not in A. Good, yeah. So how can I get the probability of C? Add them. Yeah, just need to add them together, right? If I take everything in C that's in A and everything in C that's not in A and put it together, I get everything that's in C, right? So I just need to add those two numbers together. No, it's because they're complements, right? It's not because A and B are some magical sets. It's because we have complements of each other. What do you got? 11/16? Do you think you're going to do anything different for the next part? No, it's going to be the exact same thing. We're just going to replace the C with the D, right? Yeah. So for the next part, your probability of D given A was 1/4. Replace your probability of D given A with our formula. And again, we were given that probability of A was 1/4, right? So I multiply both sides by 1/4, I get a 16th. And again, do the exact same thing for D given B. Is that an 1/8? Is that what they gave us? Yeah. So again, they give you probability of D given B. Use our conditional probability formula to rewrite that conditional probability. Probability of B again was 3/4, so I multiply by the other side, we should get 3/32. Assuming I've done my arithmetic correctly. So then again, how can we get probability of D? What do we want to do with those two numbers? Add them. So your probability of D will be an 1/8, not an 1/8, a 16th. Looked at the wrong number. Over 3/32, which gives you 5/32. Finally, what do I want to do now?
Add probability of C, probability of D.
Good. We'll take our probability. Remember, up here, we were trying to compute this number up here, right? I'm trying to compute this way up here. So we'll have 11/16 plus 5/32. What is that, 27/32? Yeah. What's the probability of B equal to? 3/4. So I got to clear my fraction, right? I got to multiply both sides by 3/4. So 3/4 times an 1/8 is 3/32. Right? I'm going to multiply both sides by 3/4. So I get 3/32. Yeah, I'm just multiplying the number to the other side. Questions on that one? Other questions on that one? We all seem very excited about them. Just want to make sure that we're playing around with the formulas because we're going to be doing more with conditional formulas. Well, not only in this section, but we'll do more with these formulas as we go along in the next couple of sections. So let's look at the next problem. This one's going to be more interpreting what the heck's going on versus just a straightforward application of formulas. So a town has 11 holidays and 10 parades. 3 of the parades occur on holidays. Wants us to calculate the probability that there will not be a parade on a randomly selected day, given that it's not a legal holiday. So we want probability of not a parade given not a holiday. Let's write it out in words rather than trying to come up with letters to represent the different pieces. Probably just as easy here to do it this way. Again, the given information is what goes in the denominator, right? So what number should be in the denominator of your fraction? And how'd you come up with 354?
365 minus the legal holidays.
Good. So there's 300. It tells us to assume that we're not in a leap year, right? We're in the regular old, unfancy year, if you will. It's not a holiday, so we're randomly selecting something that's not a holiday. There's 11 things that are holidays, so the rest aren't. Good. Now, in your conditional, what I use well, this is actually given you would know. Hopefully, you would know something's wrong pretty quickly. Would I just use 355 in the numerator? Would I do the not parades and subtract the 10 off the total? Would I just put 355 in the numerator? No. Okay. Think about why not. First, 355 over 354 isn't a probability, right? 355 over 354 is bigger than 1. If you're calculating a probability and you tell me a number that's bigger than 1, you're gonna get ready and cut your paper. Guaranteed. Okay. If there's one thing that you should know for certain is that if you get a number that's bigger than 1 and you're computing a probability, you know the answer is wrong. Okay. Now maybe it's the case that you can't figure it out. You're like, I know this is wrong, but I don't know what I did wrong. That's fine, but you should absolutely know probability greater than 1 is bad. Okay. Super bad. All right. So I wouldn't just take my 365 minus my 10 because it doesn't make a legal probability. Now remember, it's not just, the numerator is not just number of ways this can happen. It's the number of ways that this and this happens at the same time, right? It's an and on top, right? I need not a parade and not a holiday, right? So out of those 354 days that aren't holidays, how many of those days have a parade in them? 7, right? 3 of them occur on legal holidays, so the rest have to occur on the non-holidays, right? So what goes in your numerator then? 347. Good. Okay. Yeah. All right. So first thing I said was, how many parades occur on non-holidays? How many total parades occur on non-holidays? 10 parades, 3. That's 7, right? Yeah. So this is just your non-holidays minus the number of parades that are on, because we went not a parade. So we're just subtracting the 7 off. Yep. That one okay? Okay with that? All right. Look at the next one. Think about the next one for a minute or two, and then we'll chat about it. Justin.
First question, is it that like you drew 2 blue, 1 red after you drew 1 blue, or is that 1 blue included?
You're just given that in the selection there's at least one blue.
Okay.
That's the given part.
Okay.
So you're not drawing it after you drew the first blue. You're
Okay.
just
So it's given that you already drew 1 blue.
Yeah.
You
Yeah.
have 2.
Yeah. What are the chances that it had also had two, basically? Okay. That was loud. It's all right. It was just super loud. What do we do with the given information? Where does it go in your probability? In the denominator, right? Agree? Okay. So that information, if we want the denominator, we need to calculate the number of ways of getting at least one blue, right? Might be a little easier to count the complement. What's the complement of at least one blue? No blue, right? How many ways can you draw no blues? think it's more than one. If you're going to get no blues, what do you have to have? All red. How many reds do you have to draw from? And how many are you drawing? 3. So you get 4, choose 3, which is 4, right? Okay. Those are the ones that we don't want, right? So how are we going to get at least one? It's not quite 1 minus. You're thinking about the minus correctly. I need to subtract off 4, right? What do we need to subtract it off from? Not 1, but 7, choose 3, right? This is the total. So the total number of ways to choose. Why do I only want to put a fraction bar? The total number of ways to choose 3 balls from a group of 7, right? There's 7 choose 3 ways to choose balls. 4 of the ways we don't want. Right? 4 of the ways have no blues. 7 choose 3 is 35. So we should get 31 for that. There is a combinations calculator, that button on your calculators. Let me show you where it is. I can show you, but it's under the math menu. There's under the math menu. There's a PRB menu. There's factorial in there. There's all sorts of different things in there. See if I can show you where it is. If I can get the thing to run that I want, the emulator to run that I want, maybe. Oh, you're full of crap. I know it's on here because I used it yesterday in a different class. Just don't remember what folder I had it in. Oops, starting to get there. There it is. Just open. Why are you doing this? You opened just fine yesterday. Oh, for heaven's sake. It ran yesterday. I just ran it. Oh, well, anyway, I'll do. I'm going to stand there and try to find the file. Under the math menu, there should be a PRB menu. Under there, it'll say, it should have a factorial. Yeah, so the NCR is the one that you want on there. If you've got the NCR button on your calculator, if you've got an older calculator that doesn't do the fill in the blank kind of idea, you want to put the number first and then hit the NCR and then the second number. The NCR has to go in the middle. If you've got a newer calculator, when you hit the NCR button, it probably puts in a little box and a little box, and you type the numbers in there. They could have just, I guess. This is the total number of ways to select 3 balls from 7. This is no blues. If I take out the ones that don't have blues, the rest of them have at least 1 blue. Yeah, okay, good. All right. This is going to be our denominator. All right. Why did I ask this question? What goes in the numerator of a conditional probability? The denominator is the probability of the given. The numerator is the probability of the intersection, right? All right. So if I've got one set as a subset of the other, what does the intersection equal? It's A, isn't it? It's the smaller set, isn't it? All right, this will equal A. So if I know that one set is a subset of the other, I can figure out the intersection just by looking at the smaller set. Right? Now, why is that important here? If the numerator of your probability here needs to be 2 blue balls and 1 red ball and at least 1 blue ball. Right? That's the and, isn't it? One event is 2 blue balls and 1 red ball. The given information is at least one blue ball. Well, if you're looking for 2 blue balls and 1 red ball, isn't that at least 1 blue ball? Yeah. So I don't need to worry about the and part is what I'm saying. So we need, again, 2 blue balls and 1 red ball and at least 1 blue ball. That would be what the numerator of the conditional probability needs to be, isn't it? It's the probability of the intersection or the probability of the and. But certainly, if you have 2 blue balls, you have at least 1 blue ball. This event is a subset of this event. So all I really need to do, this is the same as 2 blue balls and 1 red ball. We should be able to count that, right? How many balls total are we selecting? 3. We want 2 of the 3 to be blue. How many ways can you do that? Three, choose 2. How many red balls do we want? 1. How many ways are we going to be able to do that? 4, choose 1, and then we'll multiply those, right? 3, choose 2 is 3. 4, choose 1 is 4. 3 times 4 is 12. Because 3, choose 2 and 3, choose 1 are the same. Think about why. Why would 3, choose 1 and 3, choose 2 be the same? 3, choose 1 and 3, choose 2 are kind of complements of each other, right? If I want to choose one thing out of 3, I could just not choose the other 2. It's the same counting. So I get 12. So what's your probability going to be? 12 over 31. Good. The reason why I wanted to do this one in particular, not because I wanted to think about the counting stuff, because we just talked about that in the last section, but also some of that, when you're doing your conditional probability ones, you need the probability of the intersection for the numerator. But sometimes the probability of the intersection could just be the probability of one of your events, because one's a subset of the other. And in this case, that was what happened, right? So I didn't have to worry about trying to do some fancy counting for an intersection, because one of the sets was a subset of the other. So I just needed to count the smaller set. That make sense? You're all very, very excited about the material. I love to see it. We did that one already. All right. See if you can do that one. Yeah. Anytime that a lot of times when you do get something that's at least something, you want to think about the complement. Try to count the complement. It's usually easier. I don't think it's easier necessarily in this case because at least 2, the complement of that is 0 or 1, right? But at least 2 in this case is also just 2 or 3. So I think you can probably compute it directly. You should get the same number either way. Oh, you better get the same number either way, or there's no point in studying any of this.
It's a scary thought.
If somewhere along the line we find a logical contradiction, that just causes all sorts of problems. We're ready to talk about it? Okay. So, given at least 2 are white, that's telling us what we need to put in the denominator, right? Now, again, the previous problem, we did at least 1. We counted the complement because the complement of at least 1 is what? 0, right? In this case, the complement of at least 2 is either 0 or 1. I would have to calculate both. But notice in this problem, you're only drawing 3 balls. So doing it directly, you could do 2 or 3, right? So I'm not sure it's faster to do it either way, which is why I've got the or up there, right? Let's do it both ways and see if we get the same number, okay? To break up at least 2, we need to break it up as exactly 2 and exactly 3, and we have one or the other, so we would add it. How many ways are there to draw exactly 2? 6 choose 2, 4 choose 1. How many ways are there to choose exactly 3? 6 choose 3. What? 6 choose 2 is 15 times 4 is 60. 6 choose 3 is 20. So we should get 80. Did I do that right? It was hard arithmetic in my head. All right. Everybody get 80 for the total? Or do we understand why we get 80 for the total? Let's see if we get the same way the other way. If you do it the complement, you should get the exact same number. Okay? Total number of ways to draw 3 balls out of 10. It's 10 to choose 3, right? That'd be the total number of possibilities for drawing. How many contain no white ball, or excuse me, no white balls? 4 choose 3, because it all had to be red. How many ways are there to choose exactly one white ball? Good. No white means they have to be all red. So of the 4, all 3 of them had to be. You get 4 to choose from and 3 reds. If it's exactly 1 white, there's 6 out of to choose from. So 6 choose 1. The rest have to be red. 10 choose 3. Let's see, what is that? 3 times 4. 3 times 4 is 12. 120. So you'd have 120 minus, that's 4, minus 6 times 6 is 36. I get 80. Whew. My brain hurts. It's a lot of arithmetic. Are we okay with the size of the sample space? Either way that you did it, are you okay with the size of the reduced sample space, I should say? The number of ways to get the given, right? Okay. All right, remember again, for conditional probability, your numerator is an intersection, right? But is the event you're looking for a subset of the given? Yes, just like the previous problem, right? We want at least 2 white, and we're looking for 2 white and 1 red. That is a smaller condition than just getting at least 2 white, right? So we just need to calculate 1 red and 2 white. How do you get that number? Good. 1 red out of 4, 2 whites out of 6. 4 times 15 is 60. So your probability in this case will be what? 60 over 80, which reduces to 3/4. Is that okay? Hard part's counting it, right? Once we get them counted, we just need to make the fraction. All right. Okay, what about?
Why is it not just 1/2? Like you have the 2 balls, and then you take 2 white balls out, so 4/4. I don't.
Say that again?
Like if you have 10 balls, you take 2 white balls out, that's what you get, right? You've already drawn 2. Why don't you have 4 red balls and 4 white ones? So you're picking 1. Why is it not just?
You don't know that you've only. You have to. You're thinking about if I already have 2, then you have to pull one out of there. So that's not how we're doing it. We're not saying the probability that the 3rd ball is red. That's what you're computing. Is that the probability of the 3rd one would be red? You're not including the white, red, white, right? It just says once you've drawn 3, you know there's at least 2. You're doing it a different way. You're assuming the first 2 are white, and you're trying to get the 3rd. That's a different question that you're asking. Okay. In this case, we're saying we've already picked all 3, and of that we know that 2 of them are white. That's not we picked 2 to start with. That's what the difference is. But you're right. If you knew that the first 2 were white, the probability that the 3rd one is a red one isn't 1/2. You're exactly right. And that is a different type of conditional. But you're saying I know that I drew a white one on the first one and I drew a white one on the second one. Now I need a red one on the first one, which is a probability of 1/2. You're right. But it may not have been white, white, red. It might have been white, red, white. That's the difference between the 2. Yes. Mm-hmm. That's the complement of at least 2, yes. No, the complement of at least 2 is at most 1 because the 2 would overlap. At most 1 and at least 1 would overlap at 2. I don't want to count the overlap. The complement of at least 2 is at most 1. It's always 1 less in the discrete case. Now, in the continuous case, I wouldn't worry about the overlap in that case. But no, for the in the discrete case, when we're counting things, the complement of at most a number, the complement of at least a number is at most 1 less than the number, because otherwise I'll double count the overlap. Because those are the exact. I'm trying to count the complement. I'm trying to throw out the things that I don't want. I don't want no white ball. I don't want no white balls, and I don't want 1 white ball. So I'm going to throw them out of the total. And what's left is at least 2. All right. This one doesn't quite look like conditional, but this is actually along the same lines of the question that Matt asked. Okay. So, got a string of 12 light bulbs. 3 are defective. You're going to pick a bulb, test it, see if it's defective. You're going to keep doing that until the third one is found. So notice that the reason why this is in the conditional probability section is because once you pick a bulb, are you going to pick it again? No. So say the first one was not defective, you still had 3 defectives in the lot, but you only have 11 to choose from next, right? So it changed the sample space because you're pulling them out one at a time. So we want the third defective bulb to be the third one tested. Let's do A first, so that one's a little bit more straightforward. B and C require a little bit more thought. So if the third defective bulb is going to be the third tested, what had to happen? Yeah, the first and the second one and the third one were all defective, right? So for part A, what's the probability that the first bulb is defective? Yeah, the fourth. It's 3 out of 12, right? Now, given that the first bulb that you drew was defective, what's the probability that the second bulb is defective? Given that the first one was defective, because you're trying to do 1, then 2, then 3, right? So to get the probability for the second one, I have to be given the first one's defective. What's the probability the next one is? 2 out of 11. And since we're doing one after the other, what are we going to do with the 2 probabilities? Multiply, right? Because the adding is OR, right? We're doing one after the other. We'll multiply, so we'll get 2 out of 11. Now, again, for the third one, given the first one was defective and given the second one was defective, what's the probability the third one's defective? Okay. So what we're using here is, remember we said the conditional formula is this, but we also said that we could rearrange this and get the probability of the intersection is probability of B times probability of A given B, right? So this is actually the property that we're using. Think about it this way as an intersection. I want, just for the first 2, I want first it is defective and second is defective, right? Or vice versa. This is probably the first is defective, probably the second is defective, given the probability that the first is defective. So that's what we're multiplying. Basically, we're just doing repeated application of this, right? That okay? All right. So this next one, it says, what's the probability it's the 5th bulb tested? This one's a little bit more challenging. Let's think about why it's a little bit more challenging. remember the third one is found at the end, right? So the fifth one had to be defective. So let's do that first. If we're doing the fifth one is defective, and it's the third defective, I've already chosen 4 to start with, right? So how many? 4. I've already chosen 4, and I've already taken out 2 of the defectives, right? Agree with that? Okay. So what's the probability that that fifth? Once you do that, that's the given information. What's the probability that that last one's going to be defective? How many defectives are left? 1. How many lights are left? 8. So that last one is going to be 1/8, definitely, right? I haven't done the first 4, right? But I said once I've done the first 4, I'm definitely going to multiply by 1/8 on the end. Correct? Because I know that I've picked 2 defective bulbs already. If the third bulb is going to be found on the 5th try, I've already picked 4 lights and 2 of them are defective. Exactly 2 of them are effective, right? Defective, right? Okay. We got to figure out how to fill out this part. Okay. So notice there's a number of ways to do this, isn't there? To take 2, pardon me, take the 2 out of the 4. It could be defective, defective, not defective, not defective. It could be defective, not defective, defective, not defective, and whatever the combinations I have, right? How many ways are there to do that? Not worrying about the probability, I'm looking at number of ways. What's the number of ways you can pick 2 defectives out of the first 4? It's 4 choose 2, right? So there's going to be 4 choose 2 ways to rearrange, essentially. Oops. 2 defective and 2 non-defective. Okay. All right. Now the rest of it is just a matter of trying to figure out what your probabilities are no matter what. Let's say you do, well, and we're going to understand why the multiplications will all be the same. Let's say you do defective, defective, not defective, not defective. That's the order. Okay? What would you fill in the blanks here if I do defective, defective, not defective, not defective? First blank will be 3 out of 12. Second blank will be 2 out of 11. Third blank will be 9/10, wouldn't it? Because we do defective, defective, not defective, not defective. So it'd be 9/10 and 8/9. Yeah, because there's 3 defective and 9 aren't. Right. This would be again defective, defective, not defective, not defective. Right? We agree with that. What if I'm going to erase my numerators? Don't do this on your paper. I'm going to erase my numerators. They don't feel like writing another line. What if it were instead defective, not defective, defective, not defective? First numerator would be 3. Second numerator would be 9, right? Because there's 9 non-defectives. Next one would be, and the next one would be 8. Is that a different set of numerators than what we just had? No. It's the same exact set of numerators, just in a different order, isn't it? Do one more. Again, don't do what I'm doing. Okay. Anybody who wants to be a teacher, don't do that. I like to demonstrate what not to do as a teacher. It's very helpful. What if we do not defective, 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 not defective? What are the numerators? 9, 3, 2, 8. Any different set? No, again, just a rearrangement. Okay, so if I go back to my first arrangement that we wrote down, which was, what did we have? I said 3, 2, 9, 8. What do you think I would multiply out in front of this thing? 4 2 is 2, right? 4 2 is 2 is 6, so I put a 6 out in front of it. Okay. This is not quite, pardon me, not quite a distribution that we're going to talk about later, but almost. If these were all the same probability every single time, rather than going down each time, this would be an example of what we refer to as a negative binomial distribution. We'll talk about that in the next chapter. Okay. All right. So let's see if we can adjust this to part C and do the 10th bulb tested. See if we can do the 10th bulb tested out of this. Remember again, there's only 3 total defectives, and you want the third one on the 10th bulb. So again, I would break it up into 3 distinct parts, just like we did here, right? This is part 1, part 2, part 3. Okay. It doesn't really matter what order you do the parts in, but I like to think about it in 3 different parts, right? Personally, I would kind of work backward. Do my last one because I know there's 1 bulb left out of a certain number. If it's going to be the 10th bulb tested, you've already selected 9, right? So what's the last thing in your product going to be? 1/3, because you've already pulled 9 balls out, right? We agree with that? On the previous 9, what have you pulled out? 2 defectives and 7 working, right? Okay. So we know our denominators start at 12 and they'll go down by 1 each time. I don't think I left myself enough room. I'm certain I didn't leave myself enough room. Right? So I start with 12 balls. Each time I pull 1, I get 1 fewer. That's the conditional part, right? I've already pulled 1 out. I got to pull another one out. I shrunk my sample space. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the 10th ball was the fact of the 3rd bulb. I see you keep saying ball. Okay. All right. Of these 9, you said 2 had to be defective and 7 had to be not defective, right? So let's just do defective, defective, and then all non-defective afterwards. If it's defective, defective, what are you going to have for your first 2 numerators? 3 and 2. And then if you do the rest are not defective down, what do we start with? 9, and then it's going to go down by 1 each time. Right? That's one way to do it, right? Defective to defective, 7 not defective, and then a defective. But I could also rearrange my D's and my N's, if you will, right? If I use D and N, and we want those distinguishable ways to do it, right? What's going to go out in front that we're going to multiply by to get the distinguishable ways? 9 choose 2. And basically, I've got 9 places in which I could pick the 2 defectives. That's where the 9 choose 2 comes from, right? There's 9 spots here. I've got to put 2 defectives somewhere in there. There's 9 choose 2 ways to do that. Does that make sense? Yes. Oh, the rearrangements. Yep. Another way to think about it is, we had those distinguishable permutations. Just distinguishable arrangements, like we did with Mississippi. There's 9 total symbols, but 2 of them look the same and 7 of them will look the same. And that is 9 choose 2. It's another way to think about it. If these were 9 different symbols, there'd be 9 factorial ways to rearrange them. Right? But I can't tell the difference between the 2 D's, and I can't tell the difference between the 7 N's. So that's another way to think about it, which is also just 9 choose 2. That okay? We have another one? We do have another one. Yay. All right, so lots of information we're given in this problem. This is, again, if you have any slant towards actuarial science at all, this is that's an actuarial science exam problem. An actuarial exam P sample problem. All right, we've got emergency room patients categorized by condition: critical, serious, stable. 10% were critical, 30% were serious, rest were stable. Then it says 40% of critical patients died, 10% of serious patients died, 1% of stable patients died. It says, given the patient survived, what's the probability the patient was categorized as serious to start with? Sounds like a fun problem, doesn't it? Okay. All right. Let's talk about pieces that we know to start with. Okay. All right. 10% were critical. So I'll use C for critical, S for serious, and then I'll use a T for stable since I don't want to try to draw 2 distinct S's. Okay. So if I do this as probability, what would be your probability of critical? Okay. Good. So the probability of serious would be, that's why there's a decimal since it's percentages, doesn't matter. Probability of serious, 0.3. Probability of stable, 0.6. Good, because it was the rest, right? All right. So there must be something here with conditional besides this last piece. We want patient survived, or didn't die, if you will, was the probability that the patient was categorized as serious. Okay? So if we're going to do this, one of the things that we would need to know is calculating the probability of survival, right? So how can we figure out, in particular, if I just selected somebody, what's the probability that someone survived? Well, I'm giving some information about the way they could die, well, the probability that they died, right? Okay. So what would be the probability that someone, I'll just write died as a D, okay? Yeah.
51 over 100.
So is it 51 over 100? Where'd you come up with the 51?
I just added up.
Okay. So you added up the percentages, and that would work if I knew that exactly that they were all kind of evenly distributed, right? But they're not, are they? Right? Okay. Okay. So let's think about how the died category is broken up. You could died and have been classified as critical, right? You could have died and been classified as stable or serious, right? So one of the ways we want to do this is break it into three pieces. The three pieces that we could break this into are died and critical, died and serious, died and stable. And why can I just write plus and not have to worry about overlaps? Well, these are mutually exclusive, right? This piece can't overlap with that, can't overlap with that, right? If you're in the died category, you're in exactly one of these three. Right? I've exhausted it out and I've broken it up into pieces, called partitioning. All right. These are now able to write these as conditional probabilities. Right? I can write this actually in a couple of different ways, but one way I can write this as, the first one is I could do probability that it was critical, and then the probability they died given they were critical. Okay? Notice that even though it's kind of disguised, because it's not written out explicitly, these are conditional probabilities. You know they're classified as critical. If they're critical, given they're critical, they have a 40% chance of dying. Given it's serious, there's a 10% chance they die. Given it's stable, there's a 1% chance they die. Those are really conditional probabilities that are here, even though it's hidden. Okay? Now I should be able to figure out each of these pieces and get the probability of death. It sounds so morbid. Oops. I know all these values now, don't I? Probability that it was critical is 0.1. Probability of death given critical is what? 0.4. Probability of survival, probability of serious is 0.3. Probability of death given serious is 0.1. Probability of stable is 0.6. Death given stable is 0.01. 0.03. 0.04 plus 0.03 is 0.07 plus 0.006 is 0.076. Anybody actually do that in a calculator? Yeah, okay, good. Good news is that at least there's not a lot of people dying. 51% was a lot higher of death, right? So at least it's not that bad. I mean, it's not great, but not that bad, right? Everybody okay with that part, how we got that? This is going to be important in not the next section, but the following when we do Bayes' theorem. We're going to do exactly this kind of thing over and over again. All right? So this is probability of death. Now we can do the other part. We want probability of serious giving not death, right? Probability of survival. Right? Okay? That's what it's asking. It says probability they survived. Survived is not death. There's only two possibilities. Okay? So this will be probability of survival serious and not death over probability of not death. We got the denominator from the previous part, didn't we? What's the numerator going to be? Well, this is going to be conditional again. This is going to be the probability that you're serious and the probability that you didn't die, given that you were serious. Notice, basically, this all we've done is flip around the given information on the numerator, right? We flipped it around. But flipping it around allows me to calculate it. serious was 0.3. We know that the probability that you died and your serious was 0.1, so it was probably that you didn't die given that was serious. 0.9. And then this is over whatever, 0.924. And then you can do your calculation. So again, this is an example, even though we didn't call it this yet because we haven't got there. This is an example of using what we refer to as Bayes' theorem. We'll talk about Bayes' theorem in section 1.5. Like I said, not the next section, but the following section. So we'll get more. If this one doesn't make sense or kind of confusing right now, we're going to do more and more examples of these later on. Okay? But this is where that conditional probability pops up in problems later on that are a little bit more complicated. So, two things. One, I want you to watch the independent events video for Tuesday. And after section 1.3, I got a few problems I'd like you to work on. 3, 6, and 12. And what is today? The 30th, so the 6th? Is that right? That's next Thursday is the 6th. Is that right? The right day? Everybody's looking at me like, I don't know. I don't know. How about 1 week from today? Whatever day that happens to be. Sound good? I think it's the 6th as well. Yeah. So, all right. Well, Groundhog Day is Sunday, so count from there. All right. Have a good one, everybody. We'll see you on Tuesday, if not before.